Dear students, in the last class, we discussed about the parallel transport of electrons in 2D nanostructures and the different scattering mechanism of electrons in the parallel transport. Today, we are going to discuss about the parallel transport of hot electrons in the quantum wells of 2D nanostructures on the application of an electric field. What are hot electrons? What are its effects? In field effect transistors and nanostructures fabricated by heterojunctions, the electrons are accelerated by the electric field, and these electrons, which possess very high kinetic energy, will be usually much higher than that of the energies of these electrons at thermal equilibrium. When electrons are accelerated by electric fields, they acquire very high velocities, and after the acceleration, the electron energy distribution corresponds to an effective temperature higher than that of the crystal lattice. This accelerated electrons in the quantum wells of the nanostructure under the application of an electric field is called the hot electrons. And the average distribution of energy is given by the equation E is equal to 3 by 2 kTe, where T is the effective temperature. Usually this energy is said to be decoupled from the crystal lattice of the material. The experimental studies have shown that the electron velocities of hot electrons parallel transport in aluminum gallium arsenide heterostructures under the action of an electric field are much higher than in bulk semiconductor structures of gallium arsenide, and that difference becomes very predominant and higher at low temperatures. Why the velocity of electron in the quantum well is increased? The increase of velocity in the quantum well is due to the quantization of electron energy in the nanostructure. Suppose, let us consider the case of two subbands corresponding to energy level E1 and E2 in a nanostructure quantum well. The wave functions of E2 have greater penetration into the barrier region, that is the doped aluminum gallium arsenide. Hence, the electrons suffer greater impurity scattering than the electron in the subband of E1. As a result, the velocity of the electrons in the lowest subband will be much higher. The parallel transport of hot electrons in quantum heterostructures exhibit real space transfer property, and the real space transfer property will be explained with the schematic diagram now. This is the band structure or band energy band diagram of gallium arsenide, aluminum gallium arsenide heterostructures. Here at this particular areas, the 2D electron gas is formed, and this is the energy band diagram, and this is the structure of the device based on RST. Here the aluminum gallium arsenide sandwiched between gallium arsenide, and this is the source and this is the drain, and this is the characteristic feature of this particular device, that is the IV characteristics. Now, if the velocity of electrons is very much increased in the quantum well, there are chances to escape some of the electrons in the quantum well. These electrons are transferred in real space from the undoped gallium arsenide to the surrounding aluminum gallium arsenide doped semiconductor. And this kind of transfer of electrons in real space is called the real space transfer of hot electrons. The real space transfer of hot electrons reduces the transit time of electrons from source to the drain, and that leads to the development of high frequency devices. In a low dimensional electronic device, electrons can be transferred from a high electron mobility material, that is gallium arsenide material, to the one with a lower electron mobility, that is aluminum gallium arsenide, when the voltage between the source and drain is increased. This type of devices shows the characteristic such that the current decreases as the voltage increases, and hence the device possesses a negative differential resistance region on its IV characteristics. Such type of effects of the devices are called the resonant tunneling effect. The resonant tunneling diode and resonant tunneling transistors are working with this principle. If the dimensions of the electron path, that is in the case of a MOSFET, source to drain length and the length of the gate, usually this distance is of the order of hundreds of nanometers. If the dimension of the electron path is less than the mean free path of the electrons, then electrons can travel without much collisions. Or this type of transport of electrons are called ballistic transport, or electrons are called ballistic electrons. The ballistic electrons can attain very high velocity with the application of very high electric field. The increased velocity of ballistic electrons in the quantum well under the application of an electric field is called the velocity overshoot effect. Due to the velocity overshoot effect, the drift velocity of the electrons can be made very higher, usually of the order of 10 raised to 7 centimeter per second, and that is very much higher than that of the saturation drift velocity of electrons. The velocity overshoot effect can be used in FETs to make the transit time of the electrons between source and drain shorter, and hence this effect can be used in the fabrication of high frequency devices in electronics.